Okay guys, so in this video we're going to talk about the physical properties. I'm going to skip through because it's all there in your book. In fact, it's in very good detail. So let me just go over it. So basically physical properties, we talk about melting point, boiling point, and we talk about solubility, right? Let's talk about solubility first. Haloalkanes are not very soluble, okay, in water, and the reason for that is because of the fact that, see, first of all, the halide, right, it's not electronegative enough to form hydrogen bonds in water, and the RH bond is not strong enough. See, basically the energy you get from solvation or from dissolving is not enough to break this bond. I'm pretty sure you guys have learned hydration, enthalpy and stuff. In fact, if you want me to quote the exact words which you will be required to write in an exam, the words are, by the way, they are not soluble in water. The first thing you think is like dissolves like, right? These are three polar, so like should dissolve like. But the reason is the new bonds formed. I'll write the exact words so that you can just memorize it or write it down somewhere. Formed between haloalkane and water molecule do not release or does not release sufficient energy to break existing bonds. So to break the existing bonds. So that's one thing. The interesting thing about this is that if you remember the first method of preparation we talked about, the preparation of sorry about that. The preparation of haloalkanes, that was this, right? ROH plus HX giving me the presence of zinc chloride and hydrogen. Remember? And we said that reaction rate is tertiary greater than secondary greater than primary. We also said that haloalkanes are not very soluble in water. But we know that alcohols are pretty soluble in water. Why? Because of the fact that they have OH, they can do all this hydrogen bonding and stuff with the water molecule. That's good. So what we do is in fact we do this in the reverse way. Okay, we try. This is a test for alcohols, and it's called Lucas test. Okay. What we do is we take HCl, where X is just Cl, we replace X with Cl, and we do this reaction. Okay, and there's something called turbidity, which is basically the form. See, when this haloalkane is going to start forming, right? It's going to form and it's going to make the water like mucky, okay? Because of the fact that it's not soluble. So that the scientific, posh way of saying it is turbidity, okay? So basically, you measure the time it takes for turbidity to occur. And since tertiary reacts fastest, you will see that it takes minimum time for tertiary. Then it takes about 5 minutes for 5 to 10 minutes for secondary, and about half an hour for primary, right? So that's another test for alcohols, because of the fact that we use alkyl halides are not very soluble. Okay, so that's the story about solubility here. Melting and boiling points, you guys have done it. It's just you guys will remember the words in the test used: intermolecular forces of attraction, van der Waals forces of intermolecular attraction, right? So van der Waals forces of intermolecular attraction. Higher the atomic mass, the more the forces are. So you want to remember that. So basically, if you have Rx for when X is say chlorine, bromine, iodine, iodine is going to have the highest boiling point, followed by bromine, followed by chlorine, because Ri will have the maximum mass. If you have the same halogen X prime, but you keep changing R, right? The bigger R, the more bigger R is, the more van der Waals forces you have. Except for branching. Now, what happens when you have branching is that, see, branching actually for the same molecular mass reduces your surface area, right? It reduces the surface area, and hence the interacting surfaces, that area reduces, right? Between two molecules, the amount of area which interacts with each other reduces, because of which the force reduces, and if there is lesser force between two molecules, that means the boiling point will reduce. The boiling point reduces or branching. Okay, so that is something else you want to keep in mind. Always write the losses or reducing surface area in your answer sheets if they ask you. That is done. Followed by what else? We can talk about haloarenes. So haloarenes, again it's the same arguments between ortho, meta and para derivatives. And you can see trends, but you cannot give reasons. Okay, reasons are hard. It's not there for the syllabus. You also want to know that para has highest boiling point generally among them because of its symmetry. Right? You have symmetry, so generally if you have something like this, this is much more has a higher boiling point than meta or ortho, because it has higher melting point because of meta or ortho, because it can be well packed compared to ortho or meta, right? And then the famous example if you learned in 11th grade, orthonitrophenol, para-nitrophenol, I'll just bring that in from now. So you guys know that anything which can have intermolecular hydrogen bonding is going to have reduced, is going to have increased boiling point, while intramolecular hydrogen bonding is going to reduce your boiling point, which is why orthonitrophenol was steam volatile, right? So you want to keep this in mind also in case they do something, they ask you with some fluoro compound or something which shows intermolecular and intramolecular hydrogen bonding. So that's pretty much it. That covers most of your physical properties. Remember to write polarity of bonds all the time. This word polarity was very important in our test. It's where a lot of people lost marks. If the teacher asks you, you know, why, for example, in fact, let me quote a question from my notebook. If you are asked, say, give me 1 second. See, now we discussed that if you have an alkane and if you have an alkyl halide, he has more boiling point because of higher molecular mass, right? But if you write only that, you will not get marks. You also have to write it's because of higher polarity in bonds. Okay, so this is where we all lost marks. Higher polarity. So this is why we all lost marks in the test, because of the fact that you want to remember that the higher polarity you have means you have a dipole, right? Which means that delta minus, delta plus. Which means this delta minus can attract another delta plus here, and you can keep going on like that, right? So there's an attraction here. So that actually increases your bond, your boiling point as well. Which is why you got to write higher polarity as well. Okay, so this is also important. Remember this, because if you just write higher molecular mass, you will get 0. Okay, so the question is I think 1 or 2 marks, and you will lose good marks, all the marks, because you forgot to mention this point. This point is actually much more important than this point, because see, a fluorine is just 8 units heavier than a hydrogen, and 8 AMU is not going to do much of a miracle for intermolecular forces of attraction, but this charge difference will do great miracle, right? So that is something you want to keep in mind. Before we move on, I wanted to add this to the previous video, but I forgot to put it in. So let me just finish that also. In the list of nucleophilic substitution reactions, we talked about RO minus, right? And now RO minus is a great base, and it's a which is a great base. It causes elimination. But that's not always true. It can also cause nucleophilic substitution, right? It can also cause nucleophilic substitution. And how does it do that? That is basically the idea behind Williamsons ether synthesis. You can see how this is coming up because an ether is of the form ROR prime, right? So if I have ROH plus say R prime X, for example, in acidic medium this will decompose, you get a negative charge, or say so RONA instead, we take RONA, right? Some salt, so this can attack here, this can leave, I'll get NaX plus RO R prime, right? So this is basically the conjecture of Williamsons ether catalyst. Williamsons ether synthesis. There is something else called Wilkinson's catalyst, which is why I keep mixing the names. But so yeah, this is basically the proposition. RONA is going to become RO minus Na plus. This acts as a nucleophile, attacks the R prime X, X minus leaves, you get RO R prime. Okay, so this is basically Williamson's idea, and it works great except for some cases. First of all, important thing, always remember Williamson's ether synthesis is strictly an you want to know that it's always an SN2 mechanism, okay? Why does that matter, you might ask? And because it matters because if I ask you to prepare this compound, okay? For example, you can always see if you want R O R prime, you can have ROH plus OR prime minus, or you can have R prime OH plus OR minus, right? So this can attack, this will get ROR dash, ROR prime, and you get ROR prime in both cases. So which one you choose? You choose based on this idea, the idea that SN2 mechanism is followed. Now the hallmark about SN2 reaction is that it's a single step mechanism and that the nucleophile attacks the carbon head on 180 degrees, right? Which means you need space around the carbon which is going to attack. So imagine if I draw out the two possible cases. Suppose this question comes to the exam, right? And you're stuck. You think there may be two possible answers, but generally all questions have only one answer. So what are you going to do about it? This is what we do. Okay, so we will take this into consideration. Right, so this was basically the ether which needed to be formed. We can either have ONA plus CH3X, this is one of the combinations, or we can have X plus ONA. Right, so just for better understanding sake, what I do is I will expand this because it's easier to see in this. I'll just put the carbons though. So carbon, carbon, carbon. Right? Plus. So okay, so what will happen in this case? So this was the case, I get plus CX, right? So I get O minus. And this carbon C. Note that this carbon is it's very beautifully placed, right? Because there is no hindrance around it, there's only hydrogens. So this oxygen, being that this is fat, even then, since there is absolutely not a room here and no crowding at all here, this O minus can attack and this X minus can leave. So this seems possible. But the other one reaction, look at this. Right? And you got CO minus. This guy has to attack this carbon. Okay? Now this carbon is hindered by this carbon, and this carbon. So he's going to have a very tough time. Although he's small, these guys are so big that he's going to have a very tough time finding that carbon. So this reaction is not done, okay? Because it's very hard for this reaction to take place. Seldom takes place, or it will take like a million years or something to take place, okay? So basically that's the deal. You always keep the nucleophile can be fat, okay? It's allowed to be fat. Nucleophile allowed to be fat. It's better if it's not, but it's allowed, okay? Allowed fatness. But substrate is not allowed fatness, okay? So So nucleophile is going to be the ONA, right? So the O and A, the R here should be the bigger one, and the R here and the RX, this should be the smallest, as small as possible. Primary will be best. Okay, this can be tertiary if you want, right? That is another important idea with Williamsons ether synthesis. Okay, so the last part of Williamsons ether synthesis is this idea that what if I wanted to prepare this compound, right? Now I have no choice. I will always get this. Oopsie, did I make a mistake? This one was wrong, right? Connect that on. Does that do the trick? Yeah, that's the problem. So it should have been like this. Apologies for that. Right, so you get 3 O and then 3 more, right? So this will attack. You should have an X here. The fact is, see, who are we kidding, right? This is a fat nucleophile and this is a humongous substrate also. There is no way this nucleophile is going to get here without, killing itself. So this reaction never takes place. So these types of substrates, these types of ethers cannot be prepared by Williamsons ether synthesis. So we're going to have to find another way to do that. Okay? So that was basically Williamsons ether synthesis. Generally, teachers like to ask one question from it. So, be thorough with it. Now, you guys must have a question in your mind right now. So you say, Hari, okay, I thought that RO minus was a good base. And you first kept saying that RO minus can only cause elimination. But suddenly now you're saying RO minus can do substitution also. So when does substitution happen? And when does elimination happen, right? This must be a doubt you have. If not, at least this is a doubt I had. Okay, so elimination versus substitution is a big deal, and it's in fact the only big deal other than mechanisms in this chapter. Okay, so understanding this conjecture is very important, and it's what we're going to be spending time in the next video, right? So see you guys in the next one.